Dear students, through this video we are going to discuss about tangential and normal acceleration. Tangential and normal acceleration. Okay, what is this parameter? You all will be knowing pretty well about this concept from the perspective of practical application. Say if you are holding your keychain in your hand and if you are rotating it, okay, just keeping the keychain in your hand and you are rotating it. So after rotation, if it happens to slip away from the finger, what happens? It will move in a tangential direction, right? It won't be revolving again after it gets released from the finger. Instead of revolving, it just goes away in the tangential direction, right? Similarly, you might have also experienced this. Okay, when you are just swinging it in your hand, you're experiencing an outward force, right? So there are two components of acceleration for this particular object that is rotating. One is the tangential and the other one is normal. Okay, one is making it move or fly away tangentially, the other one is making it go away from your hand, right? Every moment you will be feeling that it is going to go out. Okay, that is the normal component, and when you release it, it suddenly goes along the tangent. That is the tangential component. So now we are going to discuss about those two components, how to calculate that and all those things. Okay, so first of all, we want expressions for it. Okay, so I'm going to call the tangential component as AT and the normal component as AN. Okay, the acceleration. So when it is rotating, it is having two components. One is tangential and normal, and I'm naming them as AT and AN. Now we are going to see how we can get expressions for that. So for that, I'm doing with a small derivation. You can just follow along with me. So I'm considering a circular path. Okay, an object just like that keychain is rotating in my hand. So this is the circular path. Let the center of the circle be point O. Now I'm considering 2 points. Okay, I'm considering one point here and say another point here. And if I'm joining them, okay, I'm constructing like, okay, and let this be point A, this be point B. So at a given instant, say I'm putting the time as 0 as a reference. So at time 0, the object was here, and in a time delta t, the object was at location B. Fine. And let's consider this angle as delta theta, the small change in angle, and we know that change in angle is the angular displacement. So let the change in angle be a small value delta theta in a time in a small interval of time delta t. Now I'm going to see the components. Okay, so I need to have the tangent with respect to this point. So I'm drawing the tangent. Okay, let this be the tangent, and I'm considering it is having a velocity v at this particular instant. At time t equal to 0, it was having a tangential velocity v. Fine. And it was when after time delta t, it was at this point, and then it was having a tangential component. Like every point, it will be having the tendency to fly off tangentially. So at the time instant delta t, this is the tangential component. And if you are accelerating the rotation, okay, in the beginning I was rotating it slowly, then I started to rotate it really fast. So there will be an increase in the tangential velocity, right? If I'm rotating it slowly, it will be like when it is falling down, it will be falling at a distance of 1 meter. But if I'm rotating it really fast and when I release it, it may go up to 10 meters. So there is an acceleration. So the velocity, linear velocity or the tangential velocity is also increasing. So let the increase be delta v. Okay. So now My job is to calculate the acceleration along the tangent and acceleration along the normal. The two components I need to calculate. So to do that, I need some angles. Okay. So this is the tangent, which means this will be 90 degree, right? A tangent to a point. So to the radius, it makes 90 degree. So what about this angle? This is also 90. If this is 90, this is also 90, right? I'm naming this point as, say, point C. So now this is a polygon having 4 sides. So what will be the total angle? Sum of angles of a polygon having 4 sides will be just like a rectangle. What is the sum of angle? It's going to be 360. So this angle is 180, this angle is 180. So sum of, from this I can write the sum of angle AOB, okay, AOB plus angle ACB has to be 360, because the total will be 360. This is 90, this is 90, so minus 90 minus 90. So I'm going to get this value as 180, right? Fine. Now we have this angle as delta theta, that is AOB is delta theta, which means delta theta plus angle ACB equal to 180. So what will be angle ACB? Angle ACB is equal to 180 minus delta theta, right? If this is 180 minus delta theta, what will be this angle? Because this total angle is 180. If this is 180 minus delta theta, that is angle ACB is, I'm getting it as 180 minus delta theta from here. So this angle will be delta theta. Okay, that's the very first thing that we want to get. So the small angle is delta theta. Now I'm going to simply consider the acceleration in the tangential direction. So what is acceleration? Acceleration is the rate of change of velocity, right? So I'm going to calculate the value AT, that is rate of change of velocity. So the initial velocity was v in this direction. What is the final velocity in this direction? It is v plus delta v cos delta theta, right? This is the direction. Okay, the initial velocity was this. The final velocity in this direction, if I am taking the component in this tangential direction, this is v plus delta v times cos delta theta. The cos component will give me the velocity in this direction. So it's going to be v plus delta v, that is the final velocity in the tangential direction, cos delta theta, minus the initial velocity v divided by delta t. Okay, and as the time reduces, when delta t tends to 0, what happens to this angle? When the duration I am considering is very less, so this angle will also be very less, which means delta theta is also tending to 0. When an angle is, when theta is tending to 0, cos theta tends to 1, because cos 0 is 1. Okay, what about cos 5? Cos 5 is approximately 0.99 something, and when it is cos 10, it is 0.98 something. So whenever theta is tending to 0, cos theta tends to 1, which means cos delta theta tends to 1. So what will happen to this equation? If cos delta theta approximately equal to 1, so it will be v plus delta v minus v by delta t. So this v, okay, this v and v cancels off, plus v minus v. What I am left with is delta v by delta t. Okay, so the acceleration in the tangential direction is delta v by delta t. And what is delta v by delta t? That is the change in magnitude of velocity. Okay, earlier it was v, now it was v plus delta v. So delta v is the change in magnitude of the velocity divided by time. Okay, so AT depends upon the magnitude. That's AT is magnitude change in velocity divided by time. Okay, so that's our tangential acceleration. Now what about normal acceleration? I have the tangential component, now I'm thinking about the normal component. So what about normal component? So I'm going to calculate an. This is at, expression for at. Now I'm going for an. What will be an? This is the tangential component. So what will be the normal component? Normal component of this will be sine delta theta, right? Tangential and normal are perpendicular to each other. Okay, so now I'm going to talk about the component in this direction. This was the tangential and this is the normal. So the component in the normal direction is v plus delta v. So this is the tangential component and this will be the normal component, right? The normal component is then, if this is delta theta, this will be sine delta theta. So it's going to be v plus delta v sine delta theta minus, what about the normal component of v? Okay, that the component in this direction. This angle is 90 degree, v cos 90 is 0, hence there is no normal component for this particular v. Because it's going to be, this angle is 90, so cos 90 is 0 divided by delta t, the duration of time. So now what happens? I'm going to try this itself. When delta t tends to 0, delta theta tends to 0. So what happens to sine delta theta? When the angle is very small, sine theta tends to theta, that is sine delta theta approximately equal to delta theta. So when I substitute it here, I'm going to get v delta theta by delta t minus delta v delta theta by delta t. Okay, and here delta theta is a very small component. I'm multiplying it with a very small change in velocity. So this component is negligible. So I can neglect it, or I can consider this is approximately 0. So what I'm left with is an is equal to v delta theta by delta t. And in here, when I write this, what is this component? Delta theta by delta t. That is rate of change of angular displacement. What is rate of change of angular displacement? It is the angular velocity. So an is equal to v omega. Okay, an equal to v omega, or else you can write an equal to, what is the relation between v and omega? Earlier we have seen that. What is v? V equal to r omega, that we have seen in the previous lecture how we got this one. So we can substitute the omega as v by r. So this becomes v times v by r, that is v square by r. These are all the expressions for the normal acceleration. So now if you are observing this, so here the angular velocity comes into the picture. Angular velocity is the change in angle. So this particular parameter, okay, this particular parameter is basically the change in direction. Okay, this basically talks about change in direction of velocity. That's what angular velocity is. Okay, the angular velocity is its rate of change in direction. So the normal component depends upon the change in direction of velocity, and the tangential component depends upon the magnitude of change in velocity. So that's the basic difference that we want to understand. What is at and what is an? So we have the expressions for at and an. Now we can think about the resultant acceleration. When we have two accelerations, what is going to be the resultant acceleration? We have seen that in a lot of cases, say if I have one component, okay, I'm drawing it like this. This is my at, okay, the component in this direction, and normal to it I'm having an, right? So this is the tangential component, this is the normal component. Okay, normal component is the one that is towards the center. So what will be the resultant? If I have two components like this, there will be a resultant acceleration A, and if it makes this angle as alpha, what is the magnitude of A? A is given by root of a n square plus a t square. This we have seen from the very basic, like in the very first module itself, we have seen how to calculate resultant of two forces or two vectors. So a t square plus a n square will give the magnitude of the resultant acceleration. And what about alpha? That we can get by considering tan alpha. What will be tan alpha? Tan alpha will be at by an. Okay, so this is the take home from this particular lecture. So whenever an object is rotating, the object will be subjected to a tangential acceleration and a normal acceleration, and the tangential acceleration is depending upon the rate of change of the magnitude of velocity, and the normal acceleration depends upon the change in direction of the velocity. So at is given by delta v by delta t, okay, that is v by t, and an is given by v omega or v square by r, or what is the other expression we can write it from here? If I am substituting an in terms of omega, so v is, we have here, right, v equal to r omega, so I can get it as r omega square. These are all expressions for an. Any expression can be used according to the need. Fine. So we have seen all these conditions. Now we are going to think about the different cases, okay, so that this concept will be reinforced. So that's the basic properties we are going to mention about. So the first thing is that when an object is moving on a flat surface, okay, just like in the previous we have seen a car is moving on a flat surface, okay, what will happen to the case? What is the case here? Okay, now it is moving here, and we have the at component is equal to v by t. What about an? An is given by v omega, or it is given by r omega square, right? V omega or r omega square. Now for this particular vehicle, if it is moving with a velocity v and say in a time interval t, I am going to get at as this. What about an? So for calculating an, I require v and I require omega, or I can get r and omega square. What about the r in this particular case? What is r? R is the radius. Okay, when it is a straight line, what is the radius? The radius is infinity, right? The radius is infinity. So if I am substituting an, omega in terms of r, omega is v by r, so I'll be getting v square by r. So you can see here, when it is a straight line, the value of r tends to infinity, right? The radius is infinity. So automatically when this is infinity, what will be this term? The an reduces to 0. That is, when a vehicle is moving like this, it is only going to have a tangential component and no normal component. Okay. Now, when something is moving on a circle, right? So this we have seen. Now consider this one. There is a circular surface. Okay, I'm not plotting the whole circle. There is a circle, fine, and a ball is rolling down. Okay, I'm making a ball roll down with constant velocity. That is the important part. Okay, I'm making it roll down with constant velocity. When the velocity is constant, what happens to the acceleration? At is change in velocity by time. So in this case, if constant velocity, that's an important thing, constant velocity. If the velocity is constant, acceleration will be 0. That is, at will be 0 because there is no change in magnitude for the velocity. But what about an? An is given by v square by r. So if it is a curved path or a circular path, it's going to have some radius. Okay, let the radius value be r. Then we will be having the value of an but no value for at. Okay, so there is no tangential acceleration in this case, but it is having normal acceleration. Fine. So these are the main two things that you need to take care of. And there is one more thing that you need to, you can assess by seeing this expression. What is the direction of the component of normal component of acceleration? Okay. We have seen that case, right? Earlier, when this was the case. Okay, the tangential component was like this. What about the normal component? The normal component was towards the center, right? The normal component was towards the center, which means that this normal component of the force, that is AN, is perpendicular or normal to the velocity, right? Normal to the velocity and displacement. Okay, this is the direction of velocity. The object is moving in this direction and the normal component is perpendicular to that. Okay. So hence the direction of normal component of acceleration will be along the radius towards the center. So this is the normal component and this is the tangential component. So this is the basic thing that we need to know about normal and tangential acceleration. Okay. So these are the three properties that you need to take care of. So the AT value depends upon change in magnitude of velocity and AN depends upon change in direction of velocity. Okay, that's it. Thank you.